Okay, so now is it clear now what A and B are decidable?
Yes.
Yes.
So the first one is very easy. The easiest one, you just can check the set of states immediately. This one you have to make a simulation. This one requires a little bit more thinking. You need to decide if your machine, input machine, takes more than 481 steps on some input. On some input. So what does it mean in some input? Then maybe
That there
Is that
exists an
yeah,
input
exactly.
such
That
that
exists. Yeah, it may be in the, for example, it could be that on the empty input it takes only 2 steps. On the input 0, 1, 1, it takes 42 steps. But maybe on the input 1, 1, 1, 1, something, it does take more than 481 steps. In that case, you have to use you have to be a little bit creative. But try to think about it, and then we discuss. Because if you give me wrong solution, that's good, because then I can explain to you why they're wrong and help you understand this thing.
Ahí toca chequear que
teacher,
solo a lo menos, a lo más uno cumple la
in the
condición.
D,
Exactly.
it's not.
Frank,
One at a time, please. So wait, yeah, okay, Nicolás, speak.
pues yo podría coger el sigma y podría generar el conjunto de potencia, empezar a simular cada uno de esos. Y pues con al menos uno que pase, pues bien.
Yeah, but you need to guarantee that your set of sequences that your set of inputs that you are checking is final, right? Because otherwise you can go whatever. Yes, so simulation is important, but you need to find a clever way to say, I do not need to consider all possible inputs. That will work, because the set of all possible inputs is infinite. And we need a finite algorithm.
Maybe we could like run one step for the first input, which can be epsilon. Then we can run 2 steps for the first input and the second input, that could be epsilon and 0, and so on.
Yes, that's the overall idea. So the idea is the following. What Elkin is suggesting is you simulate M on all possible inputs of length 481 or less. Okay, all inputs whose length is smaller than this. And if this machine ever takes more than 481 steps, it must take more than that number of steps on any input of size smaller than M. Okay.
Profe, una pregunta.
Mhm.
En ese caso, por ejemplo, cuando nosotros estamos mirando el de algunos y el de todos,
Mhm.
eh, si nosotros llegamos a la conclusión de que con todos se cumple, quiere decir que el anterior también se debería de cumplir, ¿cierto?
Yeah, in this case, not necessarily. But
O sea, de pronto no por el mismo, no por la misma máquina, pero pues sí se puede realizar.
no, repeat your question again. So maybe I misunderstood you. Tell me
Eh,
again.
o sea, por ejemplo, en el problema C, ahí decía que hay que calcular, bueno, que dada una máquina
Mhm.
M, que toca calcular si son mayores o iguales a 481 pasos. Ahí
In
está, para
on
algún
some
input.
input, yeah, but
Exacto, para algún input, no, no interesa cuál sea.
mhm.
Y el otro es que para todos los inputs esa condición se tiene que cumplir.
Mhm.
Entonces, si yo garantizo que, o sea, si yo logro encontrar una máquina que cumpla que para todos los inputs, él siempre va a dar 481 pasos,
Mhm.
quiere decir que la máquina número C existe y podría hasta ser la misma. O sea, dice que es para alguna entrada, o sea, no, o sea, hay
Yeah.
garantía de que existe. Y en el otro caso, si no existe, o sea, si no hay una máquina en el cual eh, alguna entrada garantice los 481 pasos, pues no sé, lo estoy viendo así. Quiere decir que entonces la otra máquina no existe.
So what you want when you want to use is, let's say, this algorithm to solve this one, right? That's what
Exacto.
you're. So you want to know that if it's this the case on all possible inputs.
Sí,
Say you run this algorithm, and this algorithm says no. If this guy says no, then this guy also can say no, right?
sí.
Because it doesn't take more than 481 steps of any input, then the answer to this is no.
Sí,
You
es
understand?
más o menos lo que estoy diciendo.
Yeah, that works. But what the problem is the other. If this guy says yes, this guy cannot say yes because this guy says, okay, there is some input that takes more than 481, but I don't know, I do not know which one. So from that, I cannot conclude this one.
Exacto. O sea, yo lo que estoy diciendo es que no sería más fácil en este caso afrontar el segundo caso para ya como dar respuesta al primero de una manera, de una forma más directa.
Yeah, you could do that. So you have a semi-decidable kind of strategy there. I mean, you do half of the problem with this, and then you solve the other half with this. Yeah, that could work, but you still need to solve the other half. Okay.
Exacto.
Yeah, but yeah, you're right. I get you now. Okay, so going back to this, let's see you understand it now. So the idea is what you do to solve the number C is you simulate M on all inputs of length at most 481. And most means that the length is going to be less or equal to this one. And you do that for 481 steps. Okay? So the idea is that if M takes more than 481 steps on some input, then it will take more than 481 steps on some input of length at most 481. Why? Because you need to read the input, right? It takes 481 steps. You can read at most the first 481 symbols of the input. Okay, is that clear? well, this is basically the solution that Elkin gave. Is that right, Elkin? Are you there?
So the solution is that in our machine, in the machine we are we are determining is it have more than 481 steps. We only simulated with input with an input of the length of 481 or more. And yeah.
Yes, because if you do this number of steps, you cannot read more than this number of symbols on the input. And every time that you make a move, you are reading a symbol in this case. Okay. So the argument for the next problem that some of you were actually thinking about is basically the same or similar. If m takes more than 481 steps on all inputs of a length at most 481, it will take more than 481 steps on all inputs. Okay, so you only need to check the inputs of length at most 481. And of course, how many inputs? I mean, this could take forever, right? But that's another question. How many inputs of 481 of size 181 you have on a binary alphabet? You know?
2 a la 481.
Exactly, and that's a huge number, right? But
If m toma más de
yeah, so yeah, it's a little bit more than that, but it's dominated by that number anyway. What it means is that when we are talking about decidability, we don't care about complexity. It could be a very high complexity. What we care is that it terminates. Okay. Okay, and here is.
Teacher, I don't understand the explanation for this for the D.
Because
Because it say that porque está diciendo que si uno de los inputs tiene de tamaño 481, entonces todos los inputs van a tener pasos, para todos los inputs va a haber pasos de 481. No entiendo muy bien esa parte.
Okay, so let's make it simple. How many inputs, binary inputs of size 3 can I have? One at a time. One at a time, please. So how many inputs of these inputs are over the alphabet 0, 1? How many can you have? Somebody answered right. 8, right?
Infinitos. Bueno.
No. Why infinite?
Ah, no. Entendí, fue otra cosa en la traducción.
So yeah, how many different or possible strings, binary strings of size 3 can I have?
Sí. Lo que dijeron, 8.
Exactly. So then if you are the question, so that's 2 to the 3, right? So for the other case, it's 2 to the 481. But of course, if you are saying of size at most 481, you have to make the sum, right? For 240 plus 200, 479, and so on. But in any case, the term that dominates all this is this one. This one is as big as the sum of all the others. So, okay, that answers your question, right?
No, profe, sigo sin entender.
Who is asking the question?
Yo, profe, Alexander.
Okay, so Alexander,
No.
so my question is, how many inputs of size 481 have you got? So I'll make it simpler. How many inputs of size 2 can you have? Binary inputs. Let's listen.
4.
Exactly, so it's 2 to the 2, right? Right?
Sí.
So the question is, how many inputs of size 481 can you have? Then it's 2 to the 481, right?
Sí.
Yes.
So that's what we said before.
Pero, ¿qué tiene eso que ver con lo de que la máquina acepte que para acepte todos los inputs en 482 pasos? ¿Entiendes?
But okay, so I thought you didn't understand this part. Okay, so we are going back to this, right? So we're gonna simulate M in all inputs of length and most 481 for 481 steps, okay? That's of the problem.
Así es. Para demostrar que uno de los inputs necesite más de 481 pasos.
Exactly. So this will work. You know that this is all are finite. I mean, the number of all inputs of length this is finite. And I was just asking how many inputs of size 481 you have. Of course, if it's at most 481, you have to sum also the ones by size 480, 480, 79,
No.
all of them. Okay? Okay. Okay, so let's continue.
Pero, profe, pues estamos elevando un 2 a la 4.
Esto es
Profe,
solo un ejemplo para ver como cuántas posibles combinaciones de inputs podemos tener.
Exactly. That was just to show you, because I thought you didn't understand why we said that the number of inputs of size 481 were 2 to the 481. So I was trying to demonstrate that to you with smaller examples. Okay.
sí, pero aquí solo estamos asegurando que al menos que si tenemos que dar un input de 481, de tamaño 481, pues a la máquina le tomará como mínimo 481 para poder, porque tendrá que leer como mínimo una vez toda la cadena. Pero ¿qué pasa en el caso de cuando para que tome 481 pasos para todos los inputs, ya que no podemos asegurar que todos los inputs que recibe la máquina es de 481? Puede ser como recibir epsilon o algo.
Yeah, but this is of at most. So you also include that one. So you simulate the machine on all inputs of length at most 481. That includes the epsilon one. Okay.
Pero estamos tomando una máquina, estamos tomando, bueno, la máquina universal estaría tomando como caso específico que la máquina que recibe es una que tiene como el lenguaje, que el tamaño sea mayor a 481, pero eso no aplicaría para toda la...
No. This is not what it does. You take the machine, the universal machines. This M, and the first is it does the following. If you want, I can write to write the code. Say for every input S in the set of all let's say, inputs of size n, and this is for every n from 1 to 481, and then this is simulate n on input s. You see? Well, size 0, sorry. So it's going to simulate this machine on every possible input of size n equals 1, n equals 2, n equals 3, n equals 4. For every case, this set is finite. So this is a finite number of iterations. This is another finite number of iterations. And then it simulates this. It simulates this for 481 steps. If this machine on this input stops before 481 steps, then the whole Turing machine immediately can stop and say, wait, this is not the case. For this problem, for the problem D. For the other problem, it just look for every input on this set, and when it finds one that takes less, was less of what much, doesn't really matter. At least, right? Yeah, so at least. So when it finds one of these that takes at least 481 steps, then it stops and says, yes, that's the case. Do you understand now? Because this question is about some input, or for all input, and in principle, following Nicolas' first idea, you will have to try over the set of all possible inputs, but the set of all possible inputs is infinite. But the set of all possible inputs of certain size is finite. You understand now?
Pero estamos asegurando, pero esto solo parte de la premisa de que la máquina siempre lee toda la entrada, ¿no? No puede haber el caso en el que no lea toda la entrada.
Like how?
No sé, se puede dar el caso en el que una máquina pueda tener recibir datos de más en la entrada que no.
Yeah, but yeah, exactly. But imagine if you don't read the whole input, that means that you go to a certain point and you get back, right? So, okay. Suppose that this is the input. That's actually a good question. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. So this has how many? 1, 2, 3, 4, 5, 6, 7. So this is of size 7. So then it was 7 here. So you said, okay, I need to read this at least 7 steps, and then I can do something else, right? But you say, no, but teacher, maybe I can not read the whole thing. Then you do it like this: 1, 2, 3, 4, and then you go back. But you count these 5, 6, 7. There is your 7. Even if you go back, even if you don't read, you are counting this thing. So for sure, you can determine that. You understand? You cannot go here just by doing this. You know that it's enough to check it here. But if you don't read the whole thing, it's better for you. It's better for you because then you will say, without reading the whole string, you can determine that it took more than 7 steps. If you read the whole thing, you know that it took more than 7 steps. If you read less than the whole input, you might not know, but you keep counting till n is equal to 7. 1, 2, 3, 4, 5, 6, 7. You see that or not?
Vale, pues ya lo pillo. Entonces, la idea de la demostración para que la máquina acepte todos los inputs, bueno, para que todos los inputs tengan, bueno, tomen más de pasos, ya que posiblemente no necesariamente tengan tamaño doble, que aún después de toda la cadena, faltan algunos pasos antes de llegar a los 431, ¿no?
Yeah, exactly. So it's enough to consider for example, if n was 7, this for instead of 481, it's enough that you consider all the sequences of size 7 or less. You don't care about bigger sequences, because if you take 7 steps to reading this, you will take working on this, you will take 7 steps working on this bigger one, because at least you need to cross from here to here. You understand?
Sí, profesor, gracias.
Okay, good. So guys, did you all understand this?
Yes. Yes.
Okay, good. Wait. Okay, let's check an undesirable one. This one. Does the machine accept the epsilon, the null string? Is that desirable or not?
Me huele a que no.
I think that it is not.
Yeah, it is not. Something that
Me huela que no se traduce aún. En el libro dice que no.
No, it's okay. Maybe it's a good instinct. That's very important in mathematics. It says in English, it's like my gut tells me that. So here is something interesting. There is a nice theorem, Price theorem, that says that every question about Turing machines that is like a machine independent is undecidable. What do I mean that the machine independent? Like, for example, there could be many machines that accept the null string. And that mere fact that you have that question, and if the question is not true for every machine or false for every machine, that means trivial questions, then the answer is undecidable. So if you are asking something about a machine that could be many machines that satisfy the same property, we're going to see that later. But that question will be undecidable. Okay, now that's called the Rice theorem, but we'll look at that later. But this is like so you have whenever you see a question that doesn't depend on the machine, but rather on the language, then your gut should tell you that maybe it's undecidable. And this is the case. I can write infinitely many machines or infinitely many programs that accept only the null string. Okay, so I want you to
Teacher, Teacher?
Yeah.
So this can be desirable because can be machines that loops with the empty string.
So okay, if it's decidable, how you decided?
No, I see that it's undecidable.
Yeah. So why is undecidable?
Because can be machines that loops with null string. Oh, I know. I don't. or it's not that the definition it say about that.
Yeah, it's more or less that's the idea. But I want you to think. Remember the trick we used last time? So use it for this one. That would be. I'll be extremely happy you can do it. Is like assume for a moment that you have an algorithm. Where is it? Yeah, here it is. You have an algorithm that is called null string, and it receives m, inputs m, and it returns yes if m accepts the empty string, and otherwise it returns no. And suppose that you have this. That's the trick that I always use. How can you use this to solve the halting problem? Do you understand about this assumption? You want to find a contradiction. For a contradiction, you assume that it's decidable. That means that you have some God-given algorithm that solves this problem. And you use that one to solve the halting problem. As if the halting problem is undesirable, that means that this thing cannot exist. Okay, let's try to do it here. So basically, it's the same thing that I gave you before. Let me erase this a little bit. No, but this sucks. It's really disorganized there. So you have the halting problem here, and this is m, and this is x, right? The idea is that this algorithm is going to return yes if m halts on input x. That means if the machine stops at some point on input x, accepts or rejects. Then the trick is going to be the following. You take n prime and you build a new machine from m and x, and you return empty string of n. Sorry, I call it n prime, but I don't need the prime. It can be just n. So the trick here is to, this thing you are assuming that it's decidable, so it's okay. You call it here. If you can compute this, then this will be an algorithm that can be implemented. And then you will be able to decide the halting problem. And that's the contradiction. Since this thing will be clearly implementable, that means that this one cannot be implemented. And then you get your proof. Do you understand the principle? Yes or no?
Yes, a little.
Por mi parte, no.
Okay, so
Por mi parte, no, yo me confundí.
so look, you know, have you ever programmed in Python or other languages? What languages do you know?
Python.
Sí, señor, Python.
Okay, so assume that I want to prove that you cannot implement this on Python. Okay. So what I'm going to do is the following. I'm going to you know that the halting problem cannot be implemented, right? That's what we proved in the previous lecture. This one cannot. Then I'm going to assume, to prove that this one doesn't exist, I'm going to assume that it actually exists, okay? To get a contradiction. Let's assume that it exists. Then you assume that there is a library that somebody implemented this, that God wrote this thing for you, okay? And then you go and write, okay, I'm going to take a function f that I haven't told you what this function is. But it's a function that takes m and x, this input, and transform that m and x on an n. Or probably on an n and a y. But it makes this transformation. And I could show you that this can be computed. And then you run this in such a way that empty string n returns true if and only if m holds on x. And if that's the case, that means that you have solved the halting problem. But the halting problem has no solution, that there is a contradiction. And then this thing cannot exist. Because if it existed, it will generate a contradiction. And we don't like contradictions. That's the principle. So what you need to do is to find an n such that n accepts the empty string if and only if m holds on x. Do you understand that? If m holds in x when this happens, then you are solving this problem. But of course, the trick is to be able to find this n. Do you see my point or not?
Sí. ¿Esa función no sería la misma que vimos en la clase pasada?
Similar, yes. That's the principle. But who is there? I haven't heard Elkin in a while.
Profe, perdón. ¿Elkin?
Yeah, Elkin. Are you there?
What? I'm here.
Do you understand the principle of this solution that we are trying to implement?
Yes.
We haven't said what f is, of course, and that's the difficult part. This is called the reduction. I'm reducing n from this problem. This is the last time the f, what it did was to change all the accepting states into all rejected states into accept states, right? That was the trick. That's not going to be the trick here, of course. Okay.
So we are trying to change the machine M in some way so that
exactly.
So that the halting problem is solved now. I mean.
Yeah, exactly. We want to change m into n in such a way that this holds.
Assuming that the empty string problem is decidable.
Yeah, if you assume that this is decidable and this property holds, then this problem will be decidable, you see, right?
All right.
Because you execute this and then you execute this, and see this property holds, that means that the halting problem will be solved, because that means that m holds in x. So if n doesn't accept empty string, m doesn't hold on x, and if it accepts, then it holds on x. So the trick is how to do that. Okay. Look what the machine. So sorry, I call it. We're gonna have a problem of notation here. Can you hear me well, by the way?
Yes.
Teacher,
Wait. Let me finish there. So this is the machine N. So here I'm going to explain how to calculate what F does. F is going to take M, X, and generate this machine N. Okay, now your question is what? Alexander?
Yeah, teacher, because I got by problem connection. I couldn't hear the solution. Is
No,
the
I haven't said the solution yet.
uh, so, but even know the explanation. We are saying that the problem is desirable or undesirable.
Undecidable, but we are just going to prove it. Exactly the same way
Una
that
pregunta.
exactly the same way where we proved the other problem.
Okay.
The what was the membership problem? Okay, this exactly the same way. Yes, Nicolas.
No, Regis.
Okay, so
En, en este caso, cuando nosotros definimos que M para en X, eso se vería de qué forma, o sea, no consuma ningún carácter o lo consuma en su totalidad.
no. Halt means that you reach the reject or the accept state. That means halting. The halting.
Ok, o sea, cuando lo lee, termina en un estado de aceptación o de rechazo.
No, I mean a machine halts if either holds on X, if either accepts X or rejects X. Okay, that's what halting
Ok,
means. That on the input X, it doesn't get into an infinite loop. Okay.
O sea, básicamente con Holtz es que está realizando la evaluación.
I'm not quite sure how to relate to that, but halt means to stop. Okay. So the machine holds on X if rejects or accepts the input. That's the definition of halting the machine. So a machine can accept, reject, or so you know what accepting means, right? Then you know what just reject means. So then you say a machine halts if either rejects or accepts, and then you say a machine loops if it doesn't halt. That's like the
sí, o sea, pero a lo que me quiero referir es si para poder llegar a ese estado de aceptación o rechazo, la máquina M tiene que consumir a X. O
Not
sea, es
necessarily.
necesario que consuma.
No.
Solamente, por ejemplo, le pase X y no la consume.
Yeah, it might be the case. Yeah, I mean,
Ah, ok, listo.
in Turing machines, there is not this concept of consuming a seek of an input, because you can actually you don't need to. I mean, you can go immediately to reject or accept, because you can move the head towards the left or towards the right. Okay, but but let's not get confused on that. So because we don't have time now, we need to finish this. So I'm gonna create a machine N from M and X. This machine N does the following. It's a machine that the first thing that it does is to remove whatever input Y gets from its tape. Do you understand this? N is a machine that the first thing that it does is to remove whatever input gets. It puts like blank symbols. Okay?
Teacher, I don't get it. What do you mean about it removes everything that the machines? No,
So
I doesn't get the translation.
erase means that if you get
Yeah, but what do you mean with erase what?
the input, that's what I'm trying to tell you here. So this is the input, and the machine goes and erase it. So erase it is like it replaces this with blank symbols, blank, 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 blank. Okay, that's like erase that. Understand?
But if it can be possible if the input is already the blank symbol, or why it can be the input it can start with blank symbol.
Because the input is on an alphabet that doesn't include the blank symbol. So the input cannot be blank symbols.
Okay.
Okay, so you remove it, and then you now write X on his tape. So basically what you are replacing is Y with X. Okay? So going back to this example, if my input is X here, 1, 1, 1, 1, though it goes and then replace that here with that. Okay, with 0, 1, 1, 0, 1. Okay, so first step, you remove Y. Second step, you write X on its tape, N. Basically what you are doing is, in these two steps, is to replace Y with X. Do you understand this?
And teacher, I don't get it. Why we are replacing A with X? Bueno, lo digo en español. ¿Por qué estamos reemplazando I con X bueno, la idea es que M corramos a M con la entrada X, pero M tiene una entrada I. No se puede hacer que directamente la I sea igual a X para no tener que hacer reemplazo, o por qué se tiene que hacer obligatoriamente.
Because machines, they always get an input. A machine gets an input and they run with that. And what you are doing is you replace the whatever input N has with X. Just assume that you have an input and you just erase it. So if you think you are replacing whatever the machine has on the input with an X, okay? Because the machine always has an input tape, and then you just replace the content with the other. That's all, okay? So maybe there are other ways to do that, but just let us assume, for simplicity, that that's what you do. You remove the input, and then you place it with X. Okay? Everybody's there with me? You need to focus on this because this is the most difficult part of the course, and that explains why so many people don't do so well in the final exam. So please pay attention to this. So far we have a machine N that takes the input Y and replace it, whatever input it has, with X. Okay, the third step is more important. You run M on X. Alexander, I'll go back to you to your question. Why you do this step? It has to do with a technical reason that in the beginning is not important to notice, but then you will notice that it could be important. But now what this machine does, N, is to run M on X. So it simulates M running on X. Okay? And then it's because of this part here. Number 4, it accepts Y, which was the input. It accepts Y if M holds on X. Okay? But of course, this part is complicated, but you will see the following. So look, the input, Alexander, are you there? Alexander.
Yes,
So,
teacher.
your question, as usual, was important because you say why I don't use X instead of Y immediately, because then the input will be X, and I don't need that. I need that the input of the machine is Y, because I'm gonna decide if the machine N accepts or not Y. Okay. A machine can erase a string from his input and still accept it, because to accept means to get into an acceptance state. Okay. So in third step, you run M, this machine, the original machine, on X. You simulate it. So what could happen? That this, if M doesn't hold on X, you will never reach the step number 4. You see why? Do you see why?
No, teacher, I don't
You are,
see that.
Because it is in a loop.
exactly. Because you are simulating M on X. So if M gets on a loop on X, that means it doesn't hold, then you will stay on this loop and you will never get to this point. Now, if M actually holds on X, then you accept Y. So this Y will be in the language of N. You see that?
But
Yes.
teacher, why what we are saying that accept N accept Y if the machines only run with X, doesn't run with Y.
Because the machine, I mean, you accept the input. You don't accept, when you get an input, you can do whatever with the input, but you say, I accepted or rejected this input. It doesn't matter if you change the value of the input later. I mean, the definition of a Turing machine is the machine accepts an input if, starting with this input, you get into an accept state. And this machine is starting with the input that it got, but then it erases it. Okay?
But
Everybody is confused.
but in the case N is, but in the case the inputs of N are the machine M and the input X. So if we are run and is I understand the idea is that we are replacing whatever input has M in its encoding in the language of zeros or ones, we replace it with X, and we run the machine M on X, and then if the machine if the
No,
machine M,
I think what your confusion is. You think that because this machine is erasing the input Y, I mean this Y from this input, from the tape, you are not accepting or rejecting Y. That's the mistake. So the machine, okay, let me put this here. This is N equals to F of Mx. And the machine N is a machine that does the following. Initially, this machine, you have the input Y here, right? And now, whatever I do here, this program does is to accept or to reject this Y, or be in a loop on this input, right? Then the machine, if you want, you can do little steps here, little steps there, so you don't get confused. But then you go and erase this Y, and then you write X here, and then you continue. But the initial input is Y. So you need to talk whether N accepts or not this initial input Y. It doesn't matter. Lots of machines that we have seen. It's like, remember this machine? What was the machine of 0, 1, 1, 1, 1, 1? Wait, this machine that, and I think that could be the confusion. Okay, I'm not gonna find it here. Okay, I didn't find it, but it doesn't matter. I'll tell you. Remember when we tried to count whether something was of the form AN, BN? Alexander, you remember that?
Yes, we put in the stack the A's.
Yeah,
Well, we mark the A's and then we mark the B's.
that means that you actually changed the input, right?
Yeah, but that was on the execution of the
Yes,
problem.
this is exactly what I'm doing here. It's in the execution of N that the machine does that. You get the point now?
So, teacher, if the
Wait.
machine is
This machine end does these steps. This is the execution of the machine. You understand? So the machine gets Y, then the first thing that she does in the execution of the machine is to erase its own input from the tape. The second thing that it does is to write X on its tape. That's also the execution of N. The third thing that it does is to simulate M on input X. And the last thing, if you manage to get there, is to accept Y. Okay?
teacher, so if the machine N only have as input the machine M and the input Y, where it comes X? ¿De dónde viene?
Because I am producing this machine with this M and X. This comes from the halting problem. Let me finish it because I really need to finish this. I mean, we are over time, and I don't know if some people need to go. Okay, so here, just to finish. So Alexander, just think this is the execution of the machine. You have an X, M and X, and you produce a machine N that does these steps that you have here, okay? Now, you're gonna accept Y. The only way that you get to this step is if when you are running M of X, this step terminates at some point, right? So the language can be only two cases. If M holds in X, that means that you always will accept whatever Y you got in the beginning. So if you started with this Y and M terminates on X, you will get to 0.4 and accept. See that the M and the X are the same for every N that I have here, right? So for every Y that you get. For every Y, M and X is fixed. It's exactly the same, no matter what the Y is. So if M holds in X, you will accept the Y. If M doesn't hold on X, you will not accept any Y. So if M doesn't hold in X, the language of N is going to be the empty set. And if M holds in X, then the language is going to be sigma star every sequence. Do you have questions about this? Elkin?
So it is like I have a machine M. I, in some way, ignore the input that it has, which
Exactly.
is Y. Then I run it on X, and if M halts on X, it is gonna always halt in every input, right?
Exactly. It's
And
going to accept every input.
And if it doesn't halt, it's not gonna accept any input.
Exactly. Because you see, Alexander, for any y that you get here, you run the same m on x, the same, no matter what the y you get. That means that either you will accept all y's in case that this holds, any y, every y that you get, you're going to accept it, or if this doesn't hold, you're going to reject all of them because you will never get to the point 4, because you will be stuck on this point trying to simulate forever. You get that?
I don't understand. Go.
So, teacher, that, pero entonces el problema de que si la máquina N termina un trabajo o no dependería de cuál X usáramos, ¿no? Porque
Yes, yes,
una X.
and that's the point. That's exactly the point. Of course, it depends on the x, and that's the point. But this is the m and x of the halting problem that we are going to pass. Remember that it depends on the x. So what I want you to just keep with me here. So the important thing is that the language of this machine is either the universal language, every sequence is accepted, or none is accepted. All of them or none. So these are the two possibilities, okay?
Pero entonces, entonces sí sería válido decir que la máquina N es total, aunque no trabaje con esa entrada que tomó.
No, sorry?
No,
I don't care. The n is not total. Of course, it's not total because it could run forever here. You see? But actually, that's the important thing, that it's not total. So the important thing is that either you accept all inputs or none.
Okay.
Okay, and I really need to finish this thing here. So
But I have
sorry?
kind of the same question that Alexander has. What if the machines loop forever? It is going to stay in the call of the function.
But if you hold, you do not accept. Sorry, if you do not hold, you do not accept the y, and if you do not finish here, you will not accept any y. That's what your language will be empty.
Oh, yeah, I think.
Yes, a string is not accepted is if it's rejected, or if the machine doesn't hold on that input. Okay.
Oh, okay. Yes. Yes.
So the language will be this or this. Okay.
Okay.
Entonces, el lenguaje de la máquina dependería totalmente de M y X.
Yes, and that's the important thing. That's actually the whole purpose of this thing, that depends on M and X. Because maybe you haven't noticed it yet, but then you are basically done. If the language of the machine is the empty set, does it accept the empty string? Yes or no?
Dependería de la M y la X.
No.
What was the question?
Listen to the question again. If the language of n, if there is an if there, if the language of n is the empty set, does it accept the empty string?
No. No, because
No,
it
porque
doesn't accept anything.
en caso de que
Exactly.
acepte en caso de que acepte el vacío, aceptaría todo, aceptaría cualquier otra cosa, ¿no?
Yes, exactly. So that's the
Esa es
point.
la reducción de la que estaba hablando.
Exactly, because if n is the language of n, the language of n, the language of n is empty, then this thing will return false. And this, because you know the empty sequence does not belong to n, okay? Now, and this is the point, if the language of n is equal, what do I know about m and x?
I know that M runs forever in X.
So that means that m doesn't hold.
Yes.
So you see, then this is good.
Yes.
So now, what happens is the empty string that Alexander said that actually belongs to n. What can I say of the language of n?
Es sigma asterisco, o sea, todos.
Exactly. And what happens with this sigma star? If it's sigma star, what can I say about the m and x? M on x.
M halts on every input.
Exactly.
No,
So,
sería que m para en x.
yeah, exactly. M holds on x. So I have just solved the halting problem. If this guy answers no, m doesn't hold on x. And if this guy says yes, this guy holds in x. Voila, that's the reduction. Okay, I hope you got it. Otherwise, please check the notes.
Y todo esto era para demostrar que el problema de que una máquina, la máquina universal aceptase una máquina
Exactly. So
Mm.
que aceptara.
all this was to prove that there is no way to, this problem is undesirable, to know if the machine n accepts the empty string. Because I just solved the halting problem, but the halting problem is unsolvable. Then that's it. Okay? Okay? Is that okay? Because
Yes.
okay, good.
It is okay.
Nicolas?
Sí, perfecto.
Hey, I must say that this is in a way, the best class I have done, because in other courses they never ask so many questions. But this is good, because that way you can actually understand the details of these things, which are, as you can see, a little bit abstract and difficult to accept.
Lo malo es que no todos escucharon la demostración porque tuvieron que irse.
Yeah, but there is a video, so I hope that they just...
Exactamente.
Bye, guys. I have another
Frank,
class now.
Frank, antes que
Vale.
te vayas, los de funcional me están pidiendo